Thank you. So now I recall what's construction on the standard Vrias product and permutational Vrias product. The permutational Vrias product is a semi-direct product of group H and G in power X, where is H acts by shifting of copy of multipliers from direct product, and this semi-direct product can be presented in such a form: H semi-direct product with B, where B is termed as base of various product, and H acting by permutation of copies of direct multipliers G. In general form, elements of various product can be presented in form various recursion, where sigma belongs to H, to top group of various product or active group, and the tuple of elements of base various product is in the brackets. We can see the rule of multiplication and terms of various product, of subgroups of various product. As well known, B is a normal subgroup, but another normal subgroup still was not found. Still were not found. Now we can see the concept of new construction. It's a Subwreath product. It's such a semi-direct product, semi-direct product, which acts the same as Vrias product, but it acts not on direct power of G, it acts on subdirect product. Instead of direct product, we take subdirect product, which is such a subgroup of direct product of such that for each coordinate exists homomorphism, which is projection on this coordinate. For each HE, copy of HE, we have homomorphism which do projection on this HG. It means isomorphic copy of HG is the image of this homomorphism. And the action is the same. This subgroup very same to various product. So we denoted by such symbol, such sign. If we write semi-direct product, we need to specify it each time. Now we specify it by such sign. And provided the specification of semi-direct product is established separately in each case. For example, if you take various product of ZP of adding group by modulo P, by modulo P, then we have such presentation for this. P is, it means shift from the top group, shift of P elements from the base group. From the base group, and additional condition can be applied and will specify the subgroup of direct product, which make it subdirect product. This condition can be, for example, such: the sum of residua from base is congruent to G, which is residua by modulo P. And this group will be normal too, but normal in various product of adding group by modulo P. From adding group by modulo P, not in SN, of course. But changing G, we get another group, another subgroup. It's such a generalization of diagonal group. Diagonal group is normal too. Okay. Now we see that infinite various product can be presented by infinite table of Kaluzhnin, where G2 is a group element of group of function from X1 on which acting G1 to group G2. and so on. We call group splittable if such sequence um, splits. It means that composition of homomorphism S and on B is ID, is trivial. Is isomorphism trivial isomorphism on W K from the left. Not each subgroup is splittable in various product. We can specify such group that V coordinate subgroup or V coordinate set, which can be under special condition too. This subgroup have such order n1 times n2 times and so on times nk minus 1 where n1 and ne is a degree of group of permutations. It's a coordinates subgroup on various product of infinite various product of permutational groups W. Also, we can define projective limit by constructing series of factors W by WK, whereas WK is K base of various product. And we can construct such homomorphisms. Also, the elements of various product can be presented on due to group of automorphism of regular rooted tree, which denoted T from X star, and nth level of vertices denoted xn of x0 is called nth level of tree. Sorry. We remind a definition of level subgroup WL, which was firstly presented by us in the paper of commutator subgroup and subgroups. It's subgroups of vertices which belongs to L level. Permutations of these subgroups form permutation on the set XL and form the subgroup. Split definition of splittable I have said, and also stabilizer of level is normal subgroup. Stabilizer of level is such subgroup which is intersection of vertex stabilizers. Vertex stabilizer is a stabilizer which fix all vertices from G which belongs to subtree of form Vx star. It's here condition. If U belongs to subtree V X star, it's fixed. It belongs over. It's not subtree. It's belongs to addition to this tree. Complement of this tree, but not to this tree. Then it's fixed. Then it's fixed. If it do not belongs to subtree Vx star. And stabilizer level is well known a normal subgroup too. Now we consider such a concept of decrement, which is minimal number of transposition on which permutation P can be decomposed. And we see that decrement is even, then permutation even. And such property is characteristic for decrement. And we introduce such set A tilde 1 n such that first part of collision table have a property that sum of decrements is even. Sum of decrements of this level is even. Sum of of decrements even. And sure, this property specify the subvarious product, and we denote it correspondingly. it's this subgroup also denoted by A tilde 1n, and it's a normal subgroup. The normal rank of this group is n minus 1, and set of generators of normal closure is the following. We have on the zero part of collision table trivial permutation, and the second part, the first part, two transpositions on position 1, 2, on second generator transpositions on position 1, 3, 1, 4, and 1n, or maybe we can shift it to transposition 1, 2, 2, 3, 3, 4, and so on. But it's n minus 1 generators, such a pairs. This normal rank was presented firstly in paper of Dashkova Olga Yurievna with Kurdachenko. As I remember, Kurdachenko used this term too. It's school of Kurdachenko. And generators and relation was studied in our paper, this paper of Rias product. We use some properties of conormality in proof of this statement. Now we can recursively define normal subgroup A tilde 2n in Rias product E n tilde 1n, which denoted by A tilde 2n. This subgroup is normal in multiple Rias product and has order n factorial in power n square divided on 2 in power n. This subgroup is sub-Rias product too, because we have not direct product in the base of this group. We have sure sub-direct product. Also, we can define a tilde 2 n square. N square without brackets here. This defined by additional condition, the sum of decrements on the of all permutational base of Rias product is even. This subgroup is normal and contains previous group which defined recursively by us, contains I A tilde 2n as normal subgroup, as proper normal subgroup, because there are n tuple of decrement of n, sum of n decrements even, but in this group only all n square decrements even. We have n factorial embeddings of first group and second group, and different embeddings. And also we can generalize it to n tilde k n power k, which defined by following condition. Absolutely similar. Also, n tilde k n power m, and the following quotient n tilde k n power k by n tilde k n k minus 1 is isomorphic to z square, to z2, sorry, z2. We can define a more difficult group which have m minus k, k minus m levels non-trivial permutations, k minus m last levels, and the following condition on these last levels holds. Following condition of parity of decrements parity, of sum of decrements parity. And if we have such a group A tilde greater than m n power k, we can see that such sub-Rias product is normal subgroup of A tilde greater than m and k. And if we recall what is saturation set, but it was concept was presented by Alexey Shlepkin firstly in Lvov on conference on Lvov, Lvov conference. We see that that this subgroup belongs to saturation set. This subgroup A tilde K and K belongs to saturation set of case level, of group case level. We can define topology due to the level subgroup and which is coordinate set with a condition defined for the A tilde K and M. If we consider the following subgroup WK, which defined by such a various product, we can see this subgroup is normal. And also we can define pairs like V tilde LK, whereas A on the else coordinate we have sub-various product A tilde L and L, and the same on K coordinate. And we can factorize, make factorization of W, and it will be a direct product Z2 on Z2 if we factorize by this subgroup. And the intersection of such neighborhoods or kernels give us homomorphism W by intersection of WK to countable direct product of Z2, which is countable direct product Z2, and this is topological group is homomorphic to counter set. But it's only if we use intersection of the subgroup. If it was trivial intersection, it was disjoint property, but there is no this property. And we consider the subgroups. If A, K, and M is subgroup of stabilizer of else vertex of else level number E, then if KL minus L equal to M, then this subgroup A, K, and M is normal subgroup of stabilizer, as well as A, K, and M is normal of WK. Otherwise, we have transitivity of normality. We know that this one is stabilizer is normal, and A, K, and M is normal in this case too. Now we introduce another type of normal subgroup. It's T tilde N1 as generalization of diagonal subgroup. And this subgroup have two types of elements, E0, P1, Pn1. It's a table on which first part has a property that each PE is even permutation. And this table belongs to subgroup E, various product AN. And second type of permutation is a set of tables such that P1, Pn from first part of tables is odd permutation. So it belongs to Sn without ion. And these two classes form subgroup. The structure of the subgroup is such semi-direct product, and taking into account that Z3 isomorphic to A3, we can write it and generalize it for case N. For case N, instead of Cn, we write An. And this homomorphism from C2 to the automorphism group N direct product An induce a parity of permutation, change the parity of permutation, and make it even or odd. Subgroup T tilde N is normal in various product SN. Elements of first type Tn form subgroup E various product An. The subgroup EN is the monolith of various product Sn with Sn. And in general case, subgroup T and tilde has a structure of such a semi-direct product. Also, it can be presented in form of subdirect product of Sn with a special property defined on the previous items. But firstly, I introduced as a semi-direct product. In three multiple various product Sn, 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 we can consider the similar subgroup T tilde n square if it consists of elements of the form, elements with Tableau presentation, wherein E with the following decrement K 2K plus 1, decrement of PE is 2K plus 1, and decrement of the first type of sure is even. And the next subgroup can be defined recursively. It was T tilde n square, but it's subwreath product E with Tn tilde, Tn with tilde, not n square, and be denoted Tn2, Tn T tilde 2n, and have the following structure. The following isomorphism T tilde 2n has the structure of direct product of such subdirect products. Furthermore, we can see that T2n is normal subgroup in T2n square. Note that Tn T tilde 2n vertex permutation of Tableau's third part satisfies the condition P E G S n without n, or either all PEG belongs to complement of n in Sn, or belongs to In, second item, and E1 belongs to interval from 1 to n, I2 belongs to n1 n plus 1 to 2n, and Ens belongs to interval n square minus n plus 1 till n square. The set of collision tables with a vertex permutation in Tableau's second part satisfying the condition that either all PEG belongs to complement AN in Sn, or all PEG with index 3 from the third part of collision table belongs to AN. So we have the following series of inequalities, which holds in Tn square 3 with tilde. And furthermore, Rn tilde K and K forms normal subgroup in stabilizer from of cast level, which contains a proper normal subgroup of cast level if n is even, congruent 0, modulo 2. So in case of n is even, we have that this subgroup contains T tilde with index k. I'm sorry, I have to change just a moment. I use just a moment. Just a moment. Use some a little other slides with all pictures. Maybe some questions. Somebody have some questions. I open. Oh, I see the picture. Just a moment. I make changing picture.
Some questions or remarks in the meanwhile?
Do you see portrait of automorphism?
Yeah, I see that.
Yes, yes.
Is presentation or by portrait of automorphism of the following normal subgroup: T tilde S3, various product S3. We see first level has trivial permutation. On second level, we have permutation from T3 tilde. It means all of them are even. Permutation, all of them is odd. And second, on third level, we have arbitrary permutation from S3. Such subgroup is normal. The next subgroup, we see the blocks. On the third level, we see blocks by 3 vertices. It means it's a subdirect product A tilde 3. A tilde 3. If it was 9 permutations together, as here, it was subgroup A tilde 9, T tilde 3, whereas product A9. And this subgroup is greater than this subgroup. This is a proper subgroup, is also normal. The both of them are normal, and this subgroup belongs to saturation set, because all of subgroups of third level with such property belongs to this subgroups. Is more wider subgroup. Also, such subgroup, we see, can be such subgroup A3. It means all permutation is even. And generalization on four multiple, force multiple real product. Okay, and here is the definition of A tilde K and K. I have introduced it. And we have the following isomorphism. The quotient A tilde K and M by A tilde K and M minus 1 is isomorphic to Z2. A tilde K nk by A tilde K and M is isomorphic to Z2 in power nk minus M and minus 1. And we have the following normal series of level subgroups. LK means level subgroup. It's greatest subgroup, which form one of subgroup from saturation set, and other subgroups contains in this subgroup, which according to the definition of saturation set means that this subgroup is one of class of saturated set. This is such subgroups. And it says that group G is saturated with groups from the set R if any finite group G is contained in group of G that is isomorphic to some group in R. If any subgroup from G is contained in a subgroup of G, which is isomorphic to the sum subgroup of R. So R they have subgroup A tilde K and K, T tilde K and K, and sure direct product of Sn from which has n in power K copies or multipliers. It's such saturation set. Firstly, the concept of saturation set was presented by Alexei Shlepkin in thesis in Lvov in 1996 year. And in sometimes it characterized whole group, for example, infinite Lie group, by saturation set, if it's saturated by the following subgroups. And we have the following saturation subgroup. It's not level subgroup, it's whole subgroup of M multiple various product. It's T, A, N, K, tilde, and various product with H k plus 1, various product H k plus 2, and so on, till M, where Hg G is greater than K, Hj belongs to set Sn or A tilde N, but not T tilde, because T tilde can be only fast, because it's not invariant under action if it's not top subgroup, it's only top subgroup. Firstly, we can introduce topology, but I have shown it, and let I show the structures of subgroup Hg tilde greater than M and K, which has on K minus 1 level such subgroup A tilde and K, and determined by the following congruence. If A tilde K n, only n here index n, then sum from 1 to n decrements congruent to sum from n minus 1 till to n, and so on. We see the sum of n components or n add-ons congruent to 0 by modulo 2. The second subgroup, A tilde K n in power K minus G, here sum from m E1 to n in power K minus G. So we see sum becomes to be greater, and the number of sums became to be lesser, and so on. The number of sums increase, but length of sum decrease, and last we have only two sums, and K n in power K divided by 2 and n in power K divided by 2 plus 1 till nk of decrements is equal to 0, and it's for the case n is equal to 0 by modulo 2. And the last is a growth from the saturation set, most general group, which are characterized by such congruence. You see, this one is also normal subgroup of this level. And the following subgroups from the three multiple various product consist of 50 normal subgroups. The subgroups are the following type. E subreal product A tilde N with subreal product H, T tilde N subreal product H, where H one of this, and there are 6 subgroup. And second type, we have recursive construction. We use NE, where NE is number normal subgroup from such two multiple various product, and E as n subvarious product A tilde n square. A tilde n square. And therefore we have 12 subgroups, and also type 0 to square in some 18, and 3 type. We have subgroups of third level, which acts only on third level, and subgroups acting on all 3 levels is the following. NE from SN is subgroup of 2 multiple various product normal subgroup number E from 2 multiple various product SN, the same subvarious product with A tilde N, and the same subvarious product with A tilde N square. Thus we have in some 50 normal subgroups. Some similar
With me 5 minutes left.
In paper of Robert Guralnik, commutators of various product, but it was not for permutation, it's for the abelian and perfect group, and only commutators was described by him. And we have the following theorem: if H is a normal subgroup in a group of finite automorphism X out X star with depth K, then H contains class level subgroup P having all even vertex permutation belonging to AN on case level and trivial permutation in rest of levels. Furthermore, P is normal in a W, provided K is last active levels in out F X star. And here we see the detailed structures of normal subgroup of two multiple Brias product of permutation group of degree 3. We see its whole subgroup having such structure. And H2 we have three copy of this group. H3 H4 it was double semi-direct product. It's three multiple semi-direct product, and H5 is the similar to Heisenberg group, but it's not the same because there are in the dimension 3 on 3 we have direct product C3 C3 and sub direct product with C3 in Heisenberg group. There is sure not Heisenberg for dimension 3 but something similar, and Heisenberg group is a morphic to one of normal subgroup of cyclic group C3 on C3. So it's not far from our groups. It's the technique of differentiation of H2. We use order of commutant because order of and structure the similar but different construction of semi-direct product. The first of them appear Brias product sub-Brias product S3 and A3 tilde, and the second it was A3 Brias product S3. There is two subgroup, normal subgroup having the same orders but different structures and different commutators and in the ideal commutators. So we separated, identified, you see them structure, more detail of the commutators.
Yes, only 2 minutes left. Thank you.
And the proper normal subgroup Sn on Sm, it's the following, where we characterize it by subgroups of level stabilizer and subgroup acting on both levels. In case N4 is exclusive case because Klein subgroup give three additional subgroup, normal subgroup, and the lattice of structure of normal subgroup is the following: N is odd, we have Tn is separated subgroup, and if N is even, Tn, as I say, is a subgroup of A tilde, because Tn all even permutation or all odd, but in case number of odd permutation is even, is a product is even too, so it's subgroup of A E sub-Brias product A tilde N. And the last slide is normalizer of N Brias product AM in Brias product permutation group N in M degree is the following: Sn sub Brias product AM. I have finished. I'm ready to ask you questions.
Thank you very much for your talk. Very interesting and rich.